Okay, so back again with a thermodynamics FE type question. For this one, we're told that steam flows into a turbine at a rate of 10 kilogram per second. Note this is going to be a mass flow rate of 10 kilogram per second. So it's a mass per time, right? And 10 kilowatts of heat are lost from the turbine. So 10 kilowatts of heat is going to be Q dot or lost from the turbine. Ignoring elevation and kinetic energy effects, what is most nearly the power in kilowatt output from the turbine? So we want to find the power output from the turbine in kilowatts. So what do we do here? We know we're given these inlet and exit conditions. So let's draw a quick picture here. We have a turbine, and we know at the inlet, so the inlet is here. I'll use I. Actually, let me write the I here. So the inlet, we're given the pressure at the inlet is what? The 1 megapascal from the table. And we're given the temperature at the inlet is 350 degrees Celsius. So that's that. We're not given the quality. Then we have the exit. I'll use the E for the exit. We're given the pressure at the exit is 0.1 megapascal. And we're given that X, which is our quality at the exit, is 100%. And if you do in fraction form, it's just 1. So this is going to be important. Since the quality at the exit is 1, we know that quality, I'll write it here, quality X is defined as the mass of the vapor divided by the mass total. So if it's 1, if X equals 1, it makes sense that we have a saturated vapor, a completely saturated vapor. If X equals 1, we know at this exit we have a saturated vapor because it's 1. And if X, this is just the extra note, if X is 0, we know it's a saturated liquid. If X is 0, it's a saturated liquid. And anything between, we have a mix, a vapor and a liquid. So this is what's denoted here by the quality. This is going to be very important as we solve for the enthalpy at the exit. We know we have a completely saturated vapor. So that's that. And given these conditions, we want to again find the power output from the turbine. So what do? We're going to apply the first law of thermodynamics. So we're going to use the first law of thermodynamics. And I'll refer to the FE handbook just like I always do. I want to get used to, let me open the handbook here. I want to get used to using the handbook and using their equations specifically. So thermodynamics in the new FE handbook 10.0, if you go down, let's just do Control F, first law. First law of thermodynamics, we're told, is here. We know Q, heat, is energy transferred due to temperature difference and is considered positive if it's inward or added to the system. So in this case, if we go back to our system, the turbine, energy is lost. So it's going to be negative. So our Q, this is our Q dot, is going to be out the system, so it's going to be negative. So that's that for the heat. And work is considered positive if it's outward or work done by the system. In this case, it's going to be outward, right? So it's going to be the work that we're trying to determine, our W dot. This is the power or work output from the turbine. So now, if we go back to the handbook again, this is the general definition, but it's for a closed system. And in this case, we have a turbine. Well, you can go down. I noticed that this is for an open system. This is the right equation that we're going to use. But down here, they have for steady flow systems. And specifically for turbines, pumps, compressors, throttling valves, nozzles, and heat exchangers, and so on. So these are common systems we are analyzing. In this case, it's going to be a turbine. And the equation here is going to be this. This is the first law of thermodynamics that we will use for a steady flow system. So here, H, we have the mass at the inlet, the mass flow at the inlet. H sub I is the enthalpy at the inlet. V squared divided by 2 is the kinetic energy term at the inlet, plus G times Z is the potential energy at the inlet. The same thing happens for the exit, and we have our Qn, which is the heat, minus Q out, which is the work. It's the work that we're trying to determine, the net work at the system. This is the net rate of heat transfer into the system. This is our Q dot, which is a rate of heat transfer. So it's a rate term. This is also a rate term for work. This is what we're trying to determine in kilowatts, our W dot term. We're given our Q dot in the question, right? So using this equation, I'm going to simplify it further because we know the mass flow rate is not going to change from the inlet and exit state. So it's given as 10 kilogram per second. So if I simplify this further, what I'm going to do is take out the mass flow rate term and rewrite the equation. So we have on the left side, all right, Q dot minus W dot is going to equal to the mass flow rate. Then we have the change in enthalpy from the exit with respect to the inlet plus our V exit, the velocity at the exit squared, minus the velocity at the inlet squared divided by 2 plus our G times the elevation at the exit minus the elevation at the inlet. So close this out. The mass flow rate here is going to stay the same. That's given to be as 10 kilogram per second. And we know this is going to be the kinetic energy term. This is the potential energy term. This is the change in enthalpy. And we know from this question we're told to ignore the elevation and kinetic energy effects. So these terms are going to cancel. These are gone. So what we have left is going to be the mass flow rate. This is given in the question as 10 kilogram per second. And we know that Q dot, the rate of heat transfer in this case, heat lost, is 10 kilowatts. So we know that value. And W dot is what we're trying to determine. But before we do all of that, what's crucial here is for us to find our H sub E and H sub I. So the enthalpy at the exit and the enthalpy at the inlet. So for the exit, let's find these enthalpies. For the exit, the enthalpy, how can we, actually I'm going to do the inlet first, sorry. Let's start with the inlet. For the inlet, we have H sub I. So how do we determine H sub I? We're told here that we are given the pressure and temperature. Since we're given the pressure and temperature at the inlet conditions, we can easily determine our H sub I at the inlet using the steam tables. In this case, we're in the superheated phase. So we're in superheated phase, and if you go down, since we know we're at a pressure of 1 megapascal, since it's 1 megapascal, and it's above this temperature of 179.91 degrees Celsius, note we're at a temperature at the inlet of 350 degrees Celsius. It's above this saturated temperature, so we know we're in superheated, and if we go here, this is the temperature. We're at 350, right? So you go to 350, go all the way across to 1 megapascal, right? And we go to the H. So this is the H column for the enthalpy. So we have 3157.7 what? Kilojoules per kilogram. That's at the inlet. So that's our H sub I. So let's write that down. H sub I from the tables, the superheated tables, is going to equal to the 3157.7 kilojoules per kilogram. So we have that. Now let's solve for the exit. So for the exit, we want to find the enthalpy. So it's going to be our H sub E. We note here that the quality is going to be 1. It's 100%. 1 is the same as 100%. So it's a 100%. Therefore, we can conclude we have a saturated vapor. Saturated vapor. Since we have a saturated vapor, And we know what? We know we're at a pressure of 0.1 megapascal. What we could do is go back to our table and go to 0.1 megapascal. This would be our saturated vapor temperature. So we know that temperature, just the extra note, this is the temperature for saturated vapor at this pressure of 0.1 megapascal. This is arrived at because we know the quality at the exit. And also we can find the enthalpy at the exit. It's just going to be this value. Note here it says SAT, saturated. So it's just going to be this value. This is our saturated at this pressure and this temperature. This is the enthalpy at the exit. It's going to be 2675.5. So let's write that down. We have H sub E is going to be 2675.5 kilojoules per kilogram. And now we have everything we need in order to plug in the first law of thermodynamics. So let me rewrite the law so we can rearrange the equation. Our work is going to be our mass flow rate, and we take our H sub I term minus our H sub E term, and this is going to be minus our Q dot. So I just rewrote the equation and solved for work here. So now we have work, the mass flow is 10 kilograms per second. H sub I from above is going to be the 3175.7, 3157.7 kilojoules per kilogram, minus this value, so 2675.5 kilojoules per kilogram, minus the rate of heat transfer. In this case it's heat lost, so it's going to be the, specifically if we look above, 10 kilowatts. So it's going to be minus 10 kilowatts. And you can solve for the rate of work here, or the power. So note here the units look good. This is a kilogram per second, kilowatt. So all the units look good. We should get an output of kilowatt. So if you do the math for that, I got around, I believe, check the calculator, 4,812 kilowatts. So this is the output power, specifically the power output from the turbine, and it should be C. So let me know if you have questions. Don't forget to subscribe, like, and thank you for watching.